Now, because we're talking about lifting, the zeroth order logic, we say that I tell the data set, I tell the knowledge base something and I ask something from the knowledge base, where of course there are these sentences, and I tell something which is true, I ask something, and my knowledge base tells me it's true or false. However, we said that in a first order logic, it's slightly more different. I could say, who all is dishonest in AI? And therefore, the name is given as fetch, which is the fact that I fetch in some information from the database. I just don't ask a true or a false. I really fetch in information. So ask is a fetch. And of course, I store in information, the first order of logic. So I have still statements, but they are first order logic with the quantifiers with variables. So I store and fetch, so giving in some fancy names. The other fact that you might note is right here. This is how we were storing statements in first zeroth order logic, just an array of facts. Simple enough. First order logic is based on relations, and different objects having different relation with each other. Where did you last study it is the courses on relational databases, objects, multiple properties, having relation to other tables in the database. What is AI? Some kind of data mining over these databases. So, because it's this relations, how are they stored? Exactly same as databases. So, indexing, lattices, whatever is stored in in databases and data mining is an efficient way to really store and fetch information. Otherwise, even if you have all facts satisfied, you fire a query similar to SQL query, who all cheated in AI. Answer is what will be after those rules and stuff like that. All the algorithms will happen, but every algorithm is basically into a database. So if your database is not nicely stored, you cannot expect computational efficiency. And because it's another course, so we will not be looking around those efficiency constraints in any magnitude. So once unification is done, I can really cruise through the algorithms, nothing to teach. So forward chaining. How is it different? If you have anything which says for all, simply neglect it. We'll take care about it in substitutions. So, like last time, I applied a rule. We actually did a rule of forward chaining using the example of a generalized modus ponens. It was forward chaining. We took a generic rule and we applied substitution such that the rule is satisfied, the premise is satisfied in the knowledge base, and we derive the consequent. Simple enough. I did not write down for all over there. That's exactly what you do. So, nothing really to say it. I can straight away come to the formula because generalized modus ponens is only what we will be doing. So, it's forward chaining over my knowledge base where I need to tell the truth of a specific goal, which is alpha. So I apply some substitutions for all substitutions such that my substitution theta applied to the premise of the general rule P1 and P2 and Pn. So I want to somehow make the premise true, is such that I get P1 dash, that's exactly what we did the last time, P2 dash, Pn dash, which is true in my knowledge base. So last time we applied AI as C is equal to AI, R is equal to R1 because it was true in the knowledge base. That may not have been the only substitution possible. So I apply also substitution. It may be null, this loop may not execute for a rule, that's absolutely okay. And if this does apply, then I infer Q dash, which is of course the same substitution theta applied to the generalized rule. So this generalized modus ponens. And once I do that, once I get that, I simply add it to my new knowledge base. So it's a new knowledge base, so of course I'll take new as empty initially, and I'll apply this for all the possible rules. Now with the rules, one thing which may happen is that the rule may have a x, and x has already been used. For all R and C, 10 rules have for all R and C, they've already been used and they occur. So I just rename variables such that they do not occur. So it's called as the standardized variable names. You don't really need to care about it much for the rules R. And R is such that P1 and P2, Pn implies Q. So I just rename the rules, and after I rename the rules, I apply this up, and that's exactly what we were doing. So it's a ditto copycat of the same in the zeroth order logic. And of course, I will have to give you a breaking condition as well. So my breaking condition is, of course, I add new to KB. I should have written that before. So of course, I'll have to give you what the breaking condition is. And the breaking condition the last time was if Q dash is equal to alpha, then I return true. Now instead of true, I'll have to return the substitutions which are made. That's the only thing which is different. And of course, I cannot use equality in the first order logic. So I will say if theta is equal to unify Q comma alpha, which is my goal. So whatever substitution makes Q and my goal satisfiable, I return that substitution. Who is dishonest in AI? 2 is dishonest in AI. So the substitution is R is equal to 2. Rule number 2 is dishonest in AI, so I return that substitution. I may have reused theta, so let's say a phi. Standardized variable, that's exactly what we do, we just rename them up. Okay, so that's what's the case when you add something new. And if I have nothing new to add, if I have absolutely nothing new to add, then I simply return a false. What I'll do around over here is before admitting anything up, before taking anything very seriously, I will add a new constraint, which means that if I discover a fact which is already known, I do not add it to new. So if Q dash was already known, I simply say that's known by my knowledge base. So if Q dash is pre-existing in KB, my knowledge base, or Q dash is pre-existing in new, I do nothing, which means the not of that is when this is executed. If I discover something already known, I don't do anything. And of course, I cannot check it for equality. So whenever I need to do if something is pre-existing or not, if something is equivalent or not, I'll have to use unify. So I change it to a unify. Let me write it down to a complete line. So if not q dash unifies with some s in new or kb. If it does not unify, then only I add it up. If it unifies, then I do not add that up. And now my false breaking condition, if after all this, if new is null, which means I did not add anything new, then I return a false. I did not add anything new. I tried everything. I did not get anything new. And because I did not get anything new, I do this thing. This will be while forever. So I'll just repeat the code one after the other. So I put everything inside an infinite loop. I take a new and I apply all the rules, and whatever those rules tell me new about it, I add to a new variable new. If I don't find anything new, then I return a failure, and my new becomes a part of the new knowledge base. So every time I apply a rule, I of course standardize the variable and I try all the substitution. They may be multiple, which make my premise true. If my premise is true, I resolve the consequent generalized modus ponens, and when I get my consequent satisfied, I just check that it's something new that I did not already know of. And my true condition is that, of course, if I get the goal unified, then very good, I return that. So, and of course, this is this loop ending, this is this loop ending, and this is this loop ending. Just follow the book. The pseudocodes are better when given inside the book. Now, again, you'd probably like to know that everything is okay, but how is this program doing? So, in terms of complexity, let us see. First, let me make an assumption that the input is a data log, which means there are no functions, which means there are no infinite objects. I cannot apply best friend of, best friend of, best friend of, best friend of infinite times. Okay, so what do I have? I only have relations. So the relations are something like if something comma something comma something comma something comma something. So let it be a arity of n. So, and let's say that there are how many objects? Let's say there are O objects. So this could be any one of the O objects, this could be any one of the O objects, this could be any one of the O objects, O raised to power n. And how many such functions exist? Let's say there are k such functions. So this is the total number of objects. They are finite. And hence I can repeat whatever I said. Every time you discover truth value of something new, the moment you stop discovering truth value of something new, you just return a false. In the worst case, I'll discover the truth value of each one of these things. So it's not really linear polynomial, but that's because of relations which give me different permutations and combinations of objects. So it's still linear in terms of the number of objects which, it's still linear in terms of, okay, what did I write? Number of objects is what is finite. So these are which are the total number of propositions possible, which is finite. So in the worst case, I'll discover all of them. It is exponential in terms of n, which is the arity, but then how much maximum arity you believe. In our example, it was just 2 studies R1, comma AI. The interesting thing is that it's because of the number of objects. However, of course, if this relationship is not satisfied, if not a data log, then of course the number of objects could be infinite, and therefore you'll have exactly the same problem. Heuristics, more than encouraged. So use the same old trick. So try to use the best of the minimum remaining values, try to use the best of whatever, the least constraining value, the most constrained variable. Here it's actually more interesting because this is not one substitution. So I need to substitute P1, P2, P3 all the way up to Pn. That's not one substitution, that's n substitution. Here there's an order. What do I satisfy first, P2 or P1? Maybe P2 has very little options left, and most of the substitutions that P2 does, nobody has options left. So studies AI, 100 substitutions which are possible. Bad marks, only 5. So substitution bad marks will reduce most of the stuff than studies AI where you have a lot of objects. So there's an order here, there's an order in the rules, and of course there is an order in how do you apply all the substitutions, given that there are many possible. And hence it becomes a real interesting use of heuristics. The second interesting thing is again database. So for bad marks AI, comma R, I want everybody who scored bad marks in AI. What can be a quick database query? Because all my substitutions are restricted to this. I want all students who have taken the course AI, studies AI, comma R. Can I use indexing and do a very quick computational this thing? Because most of the database of course will now be large, too many objects. And that is what really makes things pretty interesting.